Hey girls, this is going to be a little preview of, remember last weekend I think you were supposed to have a homework assignment and you were supposed to watch a video. Now the last video we did was just a review of Avogadro's number. If you can remember that, then you should be okay to get started with this video. But first we need to review a chapter that even came before. I don't remember what chapter it was. Chapter 7 or something. But basically we were talking about the trends on the periodic table. We kept using this analogy of like a mother and her children getting stolen. And we talked about how you go down on the periodic table, basically the atomic radius increases. So the actual size of the atom, or the radius from the inside of that sphere to the outside, is the distance from the inside the core, the nucleus of the atom, all the way to the outside, to the outermost electron. It increases as you go down the periodic table. So not all of the elements are the same size. And then we also talked about this trend, how as you go to the right on the periodic table, they get smaller. I'm going to pretend the noble gases aren't even here. I'm just going to start with fluorine, but fluorine would be, again, and I'm not including hydrogen either right now. I'm just talking about not including the noble gases, not including hydrogen. Fluorine would be our smallest, he would have the smallest atomic radius, okay? Even though he's not the lightest. Like if you want to look at the mass, for example, he's not the least weighing or the lightest mass, but he is the smallest on the periodic table. And as you go, to this way, as you go to your left, and as you go down, the atoms are arranged in such a way where they'll be getting bigger and bigger and bigger. So if I wanted to compare, for example, sodium as an atom in its neutral state to fluorine, I know that sodium is going to be, I wrote sodium high, but anyway, I know that sodium is going to be bigger because he's more to the left, okay? So the reason I want to review this is because a second ago we were talking about converting things between moles to atoms, blah, 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 blah. Like if I wanted to say sodium, if I want to say 1 mole of sodium, and I have 1 mole, okay? And if I wanted to compare it to fluorine, and I also have 1 mole, okay? Now, do you think that they're both going to have the same weight? Do you think that they'll both have that same mass? And again, mass and weight, oh, I need to write it. Mass is just a fancy word for weight as far as we're concerned in chemistry. You'll go into the differences between the two later when you go into physics. However, for this year, every time I say mass, just think weight, okay? So do you think that a sodium atom and a fluorine atom, since you know that sodium is bigger, for example, do you think that they should have the same mass if I have 1 mole of each? And if you want to look at a real life example, that's why I went into my refrigerator, and I'm surprised Susie isn't running. She hasn't seen what I took out yet. But anyway, if you wanted to compare, if I had a dozen tomatoes and I had a dozen oranges, if I were to put my dozen tomatoes on the scale and my dozen oranges on the scale, who do you think would weigh more? Okay? Obviously, you would think that the orange would weigh more, right? What about if I only put 1 tomato on the scale, or I only put 1 orange on the scale? What do you think would weigh more? Okay? These are things you need to always keep in mind. Please keep in mind the tomato and the orange analogy when we start doing more conversions like the type we're going to do today, because a lot of students, they lose sight of the prize. Like they forget about what it is we're actually dealing with, because what we're working with on paper is so tiny and hard to imagine in your head, okay? So please don't forget that every single time you look, for example, on the bottom of the periodic table, for example, you should see in the box that sodium is in, you will have 23 point something, or 22, I think, 0.998. You will see a number below that element's symbol, right? That number is the mass of the element, okay? And we call it the molar mass. But every element's molar mass is different. And why am I saying molar mass? It's time to turn the page. Because that number, it's not if I put 1 orange on a scale, okay? That number is the mass inside 1 mole. So if I had 1 mole of sodium again, not as an ion. If I had 1 mole, well, even as an ion, we'll still have the same mass. But if I have 1 mole of sodium, then that sodium will weigh approximately 23 grams. This is, please, 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 remember, last video, when we were talking about Avogadro's number, we were talking about 1 mole having a certain quantity, a certain amount. Like if I were to say 1 dozen is 12, okay? But if 1 dozen oranges is 12 oranges, and I put all 12 oranges on the scale, I should get some mass or some weight for those oranges, right? But for you to remember, it is always 1 mole. Every number you see, every molar mass you see on the periodic table, again, that is only the mass of 1 mole of that element. Okay, so 1 mole of hydrogen as a single element would be equal to 1 gram. Now here's where it gets a teeny bit tricky for some of you guys. Those of you in class who remember already and you've been studying, you'll remember that hydrogen in nature doesn't exist like H, like that. It actually exists as a diatomic, okay? A diatomic molecule, meaning it exists as 2 little hydrogens stuck to each other, okay? So in this case, if I wanted to say 1 mole of hydrogen, all right, what I'm going to have to do is I'm going to have to say there's 2 of them. So I take that number on the bottom of the periodic table and I multiply it by 2. Ta-da! So 1 mole just means a dozen. If I were to buy a dozen and this orange and this tomato were stuck at the hip like that, not that I've ever seen that before, but if they were, and I wanted to say how much does it weigh now, well, now I'm going to have to take all dozen of both of these. I'm going to have to take I have a little piece of something. I'm going to have to take the weight of the orange and the weight of the tomato, right? Because they're stuck together, okay? So what about if I had something like 1 mole of a water molecule, H2O. How would I even begin to know what the mass is of 1 mole of the water molecule? Well, I know that if I were to look at the periodic table, I know that 1 mole of a single oxygen, just one mole, not the way it exists in nature, but just a single oxygen element, would be around 16 grams, okay?